Ladies and gentlemen, it is my great privilege to introduce Dr. Juergen Weichenberger, a distinguished leader with 20 years of experience in constructing intricate solutions that harness the power of advanced analytics, data science, database design, and other cutting-edge technologies. Let us delve into the remarkable facets of Dr. Weichenberger's illustrious career. AI pioneer and industry veteran, Dr. Weichenberger has been at the forefront of the AI industry since the mid 1990s. His journey spans diverse sectors where he has built solutions tailored to various industries. His wealth of experience reflects a deep understanding of ever-evolving landscape of technology. Vice President AI New Value Stream at Schneider Electric. In 2022, Dr. Weichenberger joined Schneider Electric as the Vice President AI New Value Stream. His focus lies in producing industry-grade solutions, bridging the realms of core algorithms, robotics, cybernetics, and human intelligence. Accenture and Senior Data Science Executive. Prior to his current role, Dr. Weichenberger held pivotal positions at Accenture. His contributions as a Senior Data Science Executive underscores his expertise in AI and data. Dr. Juergen Weichenberger's dedication to innovation and industry impact makes him a true luminary. Please join me in welcoming him to our webinar, A Beacon of Knowledge and Forward Thinking.
So while Kieran's pulling up the slides, so what have I brought today? I mean, we hear generative AI is everywhere these days, and it's praised to solve all the problems we couldn't solve in the past. I want to give you a little bit of a differentiated picture on it, what you can truly do. I brought an example of which we have just implemented, and actually will present it to the world officially next week at the Hanover Fair. But it is definitely a bit of mind-boggling how things have changed over time. And when we jump to the next slide, just a quick word, who is Schneider? For the ones who have not heard about it, we are a product company who develops products. But we have evolved a bit just from purely putting some hardware pieces together. We've learned if we want to have an impact on the world in the space of sustainability, we need to get a couple of tricks to the trade, and one of these is AI. And so this has helped us to combine the hardware and the software to help the world to become more sustainable, meaning being more thoughtful with our resources in terms of energy, raw materials, and all of that. Because believe me or not, if you're not paying attention to it, it goes away. And one of the biggest debates today is how sustainable is generative AI? And I can give you a super simple example. We all know the good old Casio calculator watch on your hand wrist. And when you tapped 1 + 1 in the watch and you did it 1,000,000 times, it would always tell you it's 2. And the amount of energy it needs is sub 1 watt. Now you can ask a generative AI the question, what is 1 + 1? And you have a chance that it tells you it's 2 because it's probabilistic. Plus, you need a GPU for inference, and that costs you at least 400 watts. So you will see we made something which was well established and super simple into more advanced with an uncertain outcome, which takes about 400 times more energy. So that's just something which has really boggled us in terms of how can we make that again 1 watt. So when we're moving on, a bit of a thing from where are we coming from and what have we done so far. If you go to the next slide, please, Kieran. One more. One more slide. So what you see here is a typical industrial setup, highly complex processes which needs a ton of energy. And the people would just have done what they have done for many years, where they were very comfortable with and how to manage this at their best potential. And now they've done this with mathematical methods, but sometimes unconsciously using already statistical machine learning methods to optimize energy consumption. But not because they took it as a purpose, they just used what they have to do. And when we go to the next slide, you will say at a certain point in 1956, somebody had a great idea about AI and ML. And I'm sparing you reading out the definitions. I think all of you know it, but it allows us to unlock additional information from data. So this was a great invention. Now, how has this invention affected industrial applications? When we look at the next slide, you see a typical topic of real-time optimization. So you run something, you build a car, you want to do it in the most efficient ways. You have lots of controllers, you have lots of data inputs. But what it is it reacts to what has happened. So it's not forward-looking. So what we want to achieve is we want to get out from a reactive into a proactive mode, similar to what we said in the medical environment. If the cancer is there, then we have to deal with it. If we can find the precursors before it actually starts, we are well in a better position because we can have better treatments, we can spare the patient from lots of suffering. It's a similar thing in the industry. You want to get from reacting to proacting. So we did a step forward, and when we look on the next slide, is we started to introduce machine learning into real-time optimization to make it a bit smarter. It is mainly statistical machine learning, but it helps us to get one step forward from a pure reactive into a proactive environment. So we can now predict what's going to happen 4 to 6 hours out. We can even predict with more accuracy what's going to happen in half an hour to an hour out. And it makes it a way more steady state model. But it's still, you would say, can we do more? And yes, in this traditional world, we had one more, which we can do. When we go to the next slide, as we can see, we have machine learning introduced, but what we have not introduced is the feedback. So when you think about, you detect a scenario which is X hours out, what does an engineer really want to know? So he knows something has happened. The next boggling question he has is he wants to know, why are these things happening? So what is my reason? Is it because something is just worn out? Or do I have a systemic problem? If I have a systemic problem, whatever I do at a punctual point, it will come back on me. It's these old problems of systemic problem. If you not go to the root of the problem and you just treat the effect, you're not going to kill it. It will just come back to you. So with the introduction of reinforcement learning, we were saying, okay, we know what's the problem. We'll prescribe an action, and now we can measure the outcome of the action. And we can say, actually, has this the right or wrong effect? And when we're bringing this into our thinking, we can make our actions way more accurate. And we can also adapt to a given environment, which we couldn't do before. Before, it was just really, okay, we predict something, we prescribe something, and it happens. Now we can make our predictions continuously better. So we have achieved a lot to get to reinforcement learning. But the question which is still open is, how do we generate new solutions when the input conditions change? Right now, what we would say in this step is, I need to predict the unknown. So how can we turn unknown conditions into well-defined actions? And for this, somebody did us a favor to introduce generative AI. So when we have forward, next slide, please, you will see where do we want to go now. And when we're looking here, there's a whole new branch of generative models. We have the shallow models for a long time in naive Bayes, and we have now the new deep models coming based on conditional variational autoencoders, or VAEs or CVAEs, which give us more approaches here. Then we have now brought this whole world into the unsupervised section, where we have the autoencoders and we have the Gaussian mixture models. So I have lots of friends who have done great stuff with GMMs in the past, but they're still lacking a couple of tricks to the trade. And the way we can now use the autoencoders allows us to go way deeper. And when we're now looking a little bit, I'll give you a little bit of an introduction so that the things usually most of the Gen AI companies never tell you is what is the stuff behind. And it will also then make the example I brought today a little bit more understandable than just thinking it's black magic, which is going to happen, or which is actually not happen. It's all explainable. But when we move on, so what is generative AI? When we go to the next slide, there is, let's say, I hope a definition which makes sense for everybody, but literally generative AI refers to a set of artificial intelligence AI methodologies which can produce new outputs which we haven't seen in that way before, but they can also adopt to questions. And if my students at MIT and Northeastern hear me, I tend to say if ELIZA would have had the same compute power and n-gram inputs than OpenAI has today, we would all be surprised how good ELIZA would be on today's terms with the same compute power and the same quantity of input making available to her. So I think it sets in relation how good the 1966 implementation of ELIZA already was at that point in time. And I know that the youngsters will always say, this is all bullshit. This was just some people playing toys. But often in the old days, with the limitations in compute power and input power, we had to be way more creative than what we can do today. The other good thing is that generative AI is not limited to text. We can do coding today, and that's the example I actually brought, but we can also go to images. As I mentioned in the panel discussion before, we are working heavily on LVMs. So we're not working on the DALL-E image generation side. We are working way more on the image classification side, especially classifying unknown information and labeling it, because that is what for us is really the reality, because everything is in a continuous change. And like every other image recognition solution, if you haven't seen it, if it's trained, the results get very wonky. So we really try to put a lot of stuff on it. And then you can do lots of other things like music, audio patterns and stuff like that, but doesn't, well, I still say here, this is more in the toy world than we have true industrial grade solutions. So when we go into a bit of motivation why we're using it, it comes to the limitations of which everybody else will say has, like the CNNs, RNNs, and LSTMs have. And on the next slide, I'll just give a quick outline. For example, you know, next slide, please. On CNNs, they're good at local feature extraction, but they have problems to understand long-range data dependencies. This you would see specifically when you go in time series data. And also CNNs struggle to understand order. So what is the sequence between a word order? For them, it's more like a random bit. LSTMs suffer often from the gradient problems, gradient descent problems, and has to do with the training and how to train it. And the ultimate joint suffering CNNs, RNNs, and LSTMs have together is that they have to be trained to specific input. So if you try to do what the human brain can do to process audio, visual, and other inputs like smell or taste into one system and produce an output to say, okay, what I'm seeing here is black shaped, round, is good for visual recognition. That is not that simple for RNNs or CNNs or LSTMs. You have to say, yeah, I can do the one or the other, but it is a real struggle to say, let's do all three things together and pretend you have the same power that a human brain has. So it also shows why nature still has some tricks to the trade, which we cannot replicate in a machine today. We're getting closer, but still we are not there. And one of the main reasons is, I haven't written it on this slide or in this presentation, is when you go into the foundational elements of all generative AI solution, of all neural network based AI solutions, that the main limitation is the neuron type, because that's the one thing which has not changed back to 1956. It's still the perceptron with the same basic sigmoid activation function. Yes, we have given the sigmoid function some tweaks, but it is still sigmoid in its basics. And that is what buries the brain, the master limitation or disadvantage of the human brain, because the human brain does not work in a sigmoid activation function. It is way cleverer, and that would be an own presentation on itself to talk about biologically inspired neural networks and how you make that happen and how much more powerful they can be if you can train them. But when we're going on to the next slide, so somehow Google, so it was not OpenAI, it was Google, who came up with the idea of using the transformers. And transformers per se, transformers per se were already existing, so they were not new. So it's not that we say we have here fundamental new technologies. It's just we use technology in a new way by adding positional embeddings. So we broke up the sequential nature into positional embeddings with a vector form. And who's interested, I recommend read the paper from the Google guys. It opens your mind about what happens truly in the background. And so these guys are good and they know what they're doing. And to lay this out on the next slide is a super simple example. And it's just say Alice, who has a black cat, loves going to the park. If you were to just try to put this in a normal language detection algorithm, you would have lots of challenges, because when you alone look at the structure of the sentence, it would tend to get a detention which says Alice loves black cat, or the black cat loves to go to the park, and it would lose the context. And in this case here, with the ability of using transformers, we can put the sentence in the right context without having to write a ton of complex n-grams to reflect this. So the key thing is here to the previous technologies we had in NLP, or specifically in NLU, where we had to specify the n-grams to depict the sentence into a structure which allows us to derive the sense from it. We have overcome here that we transform n-grams into prompts, which help us then to create the embeddings to understand the query and the key underneath. So it's really some clever reusing of technology to make this happen. And here again, who is in the mood, I put a bit of a GitHub example here, just hop in, try it out. You will have lots of fun working with it. And the last of the boring slides before getting into the real example is just a bit of an outline about how complex the architecture now is, which we have built around to make this work at scale. So when we're looking at the next slide, we have let's say a 6 encoder layer stacked. So 6 layers of encoder stacked above each other, and similarly 6 decoders, and then bringing in the positional embeddings and creating the mask attention levels to make that happen before this whole goes then into the softmax, which predicts literally what is the next word for the next best word for the output to put in. But you say, similar to when we introduced CNNs, convolutional neural networks for image detection, we added 150 layers, and it's the same story we're playing here. We'll have to add lots of encoders and decoders to get to a level of output which is adequate. So when you compare it with nature does it with a 5-layer neural network across the brain. Structure doesn't change. The only difference is total connections, or it can leverage total connectivity. It doesn't do it. The neurons only use a certain subset of connections, but you see we have to introduce a lot of complexity to get close to nature. And this is just what I want to give you here. Even if people talk easily about it, there's a lot of technicality in the background which you need to control. And as more technicality you have in the background, as more room for error is there. And that's also one of the reasons why we have hallucinations, is the complexity of the system, which we have to take care of. And now we are going to a real world example, which we in Schneider were faced by our customers. And believe it or not, when we go on to the next slide, or 2 slides forward, the customers essentially ask us, can you help my automation engineers to write PLC code? So PLC is so the little computers which control pretty much all manufacturing processes, or if you go in your car, you have it's called ECUs, so they control your car. If you go into an aircraft, it's the FMS, the flight management system, so flight management system, FMSC, flight management system computers, which control the aircraft. And you find them everywhere in the world. They need to be programmed and they need to be stable. And so literally we got asked, can you help us using copilots to improve the coding and stability? And then when we tested various LLMs, they all could write PLC code without a problem. The outputs were questionable at the beginning if they really work, but in general terms, they can write PLC code. The challenge is when you think about, if I do this for fun as an individual, it works quite well, because I don't need repeatability and maintainability. And this is where it starts to get interesting. When if you be a company who produces aircraft like Boeing or Airbus or Embraer or Bombardier, you don't want to have an individual set of code for every aircraft, because it becomes unmaintainable. And similarly, you don't want to have every time a new variant of the same function. And this is also where, when we're looking into medical applications in classification examples for MRIs or CT scans or simple images to detect anomalies in the scan, you don't want to have all the time a new interpretation of this. You want to have consistency and you want to have no hallucinations. And that was the biggest challenge for us, is how, when, for example, the customer wants a 10-second wait loop, that the 10-second wait loop is always the same, because it's a super basic set of code. And we don't want that the system is all the time reinventing it, and you have then 1 million versions of a 10-second wait loop. So that's one big challenge, which goes against the nature of the autoencoder. The second big challenge is customers have naming conventions. They have their ways to name things, and they don't want to change it because their teams are used to these conventions, and that's literally their lingo they're operating. And if you have an international company like Pfizer, when they have named things consistently across the business, and no matter if it's English, German, Spanish, French, Italian, Chinese, Japanese, there is a basic lingo which is consistent across the world. And you don't want, and you need to get your generative models to understand this lingo and consistently use it. And so that's also something which has not existed upfront. So we had to get this in as well and make it work. So when we move on to the next slide, you see the sequence of things we had to create. So literally we had a generate, we had an explain and document phase, we had a debug, and optimize, a translate, and an auto-completion phase. We have a bit spare translate and autocomplete because this goes then how you get something which was originally written in English into Chinese, or how you get something which was originally done in Chinese back to English or German or Spanish or French or Dutch or whatever other language you want. And auto-completion is also a bit of a risky game in that spot, so we have to think about that separately. But so you see, it's really key things is generate and explain on the one side, but debug and optimize on the other side. Debug is also interesting, is to really see if the code is error-free and works the way it's expected. Super critical in FDA-regulated environments. So when you think about drug production lines, the FDA expects that they are working consistently in accordance to what was originally commissioned. And so that is a core thing, and we have captured the first. And when we look at the next slide, you can see literally the combinations and how we literally had to go through step by step to make it work. So it was not like that we got everything in one go. We really had to go in 5 iterations, which were started with generate, went to explain, went to debug. And after debug, we had to go back to generate and explain to make it work, not to talk about optimize. So optimize us many steps out because it makes things very complex. But you also see you get a circularity in that you make changes, you need to rethink the changes and then get forward. And just to give you, or to answer, how much can it be more effective than a human? And believe me, human P&C coders are very good. So super highly developed skill sets, and these guys are better. And when we look at the next slide, that's the first set of findings we found, is that we were able to achieve about 20% more efficiency. So it's literally the time it takes from the beginning to the end to create it. And one of the key things is we could improve the quality by 6% compared to super advanced humans. And this is just simply happening because we can get more consistency and we can avoid often very simple typos, which can, when all of us who code it knows how easy it is to make a mistake by just using a dot instead of a minus, or just you have one star too much and you point in the wrong direction in the memory and so on. So the systems here really help improving efficiency, improving quality, and also creating more safety and security. And on the other side, it's just about what were user requirements to make it usable for them. So one of the biggest, when we go to the next slide, one of the biggest user requirements we had was when they ask the same question, they want to have the same answer always. And this can only be altered till it turned out that there is a newer version of the tool, and that justifies that for the newer version, the answer differs. But as long as we're working on the same basic setup, same question, same output. And the users also want to have a clear usage and performance tracking, some cross-abstraction level relations, syntax enforcement, and stuff like that. So, for example, when you think about syntax enforcement, that the variable naming is consistent and the same and not changes all the time and all these little things. So that was like all the things we had to deal with. And now, how does it look like at the end? So the next 4 slides is literally what have we done for the users. So obviously, we're in a modern world. Everything has a web interface. When we look at the next slide, this is what the user sees when he starts. He has a couple of options here, and to go into, you see we have FIFO shift register, application controlling. So we have applied this for various lines of Schneider products to make it work. But you see, this no longer looks like a Python coding environment where you write Python and you see debug buttons and lines of codes and stuff like that. So how does it be different when we're going on the next page? We had to enter a tracking system. This is a legal requirement from the FDA. For example, we have to track who has written the code or who has triggered the code ingestion. So in case that question or that prompt the person raised was wrong, we can find the perpetrator. And on the right side, you can already see the output window. On the next page, you see now the person starts to live interact with the tool and asks questions, and he gets his code output on the right side. You see here, this is now real written PLC code, the way it's supposed to be. You have a variable declaration, and then you have encoding signals who are going in there. And we have added here the explain button because explainability in the modern world is the key to acceptance. So when you work with engineers, when you work with doctors, nurses, lab technicians, and so on, if they're exposed to artificial intelligence as a black box, they have a very hard time to accept the results. If you add explainability, you change the game. That's exactly the same thing we did here. We added the explainability to the equation, and that has tremendously ramped up the acceptance rate for the solution. And on the last slide, we have just added a little reinforcement learning cycle. So that means we want to get the system to learn consistently and improve. So that means we're not just relying that we're making the same mistakes again and again and again. And having given here the reinforcement learning cycle. So you see, you can use generative AI in a meaningful fashion on an industrial scale. And yes, we've started, we are learning it. So we're taking the fancy individual application into a level where it is accepted by the body of the FDA, the outputs are accepted, and we still help the people to get quicker from A to B. And so that's where I want to open the floor for questions and hope everybody has found this interesting and useful. So I'd say thank you and let me know if you have questions.
Thank you, Dr. Juergen. That's a great presentation.
In case, if you have any questions, you can also email me or drop me a quick note or drop a note to Kieran, and we can handle it offline as well. Otherwise, back to you, Monica.
Yeah,
Actually, I wanted to comment that this is really interesting work because it's connected with with real life beyond just making things that are more explainable and that are this is the key today to be able to get approved even for a clinical or anything that is related to industry oriented projects, and very interesting talk. Thank you.
Thank you.